All right. So, hello everybody. I'm George. I will be doing this video tutorial on DynamicalSystems.jl. A bit of bio background for me. So I'm working at the Max Planck Institute for Dynamics and Self-Organization, which is in Germany. And on my pretty much free time, I have been developing this library that I will talk to you about right now. So this tutorial is separated into 6 notebooks. I hope you have found the download link. If not, then you can find it in the video description. And so without further ado, let's start. So what is DynamicalSystems.jl? It is a Julia software library for the exploration of chaos and nonlinear dynamics. And what it actually is, if you're curious about it from the Julia perspective, Dynamical Systems is a package that re-exports many other packages. So what I'm showing you here in this, let's say map, is the different packages that compose DynamicalSystems.jl. And this is actually what we will be going through in the course of this tutorial. And here you can also see the various features that each individual package has. All right? I will be going through this list one by one. But before we go into the details, let me tell you that DynamicalSystems.jl itself is part of a larger GitHub organization, which is called Julia Dynamics. And we recently got a new website, so if you think what you see in this tutorial is interesting, be sure to head over to the website. This is the website, and the other packages that we have here, and some other information that I will not be talking about in this tutorial. All right. So installation is pretty straightforward. Dynamical Systems is a registered package, so you have to enter the package manager and then just add it. And please be sure that you have version 1.2.0 at least for this tutorial, all right? In addition, I will be using PyPlot to plot some stuff and the module ordinary diff-ec to access some advanced solvers. So be sure that you have installed these as well. And here you can find the list of contents of these tutorials. And here some info about the documentation. This is the link to the documentation, and this is a list of contents. All right, so now I'm starting with the first notebook of this tutorial series, which is about creating dynamical systems. So what is a dynamical system? It is actually something very simple because it is a rule that describes how some variables evolve in time. All right, this rule or this law is encoded in what we call equations of motion, all right, which is a function. So in our case, there are 2 types of dynamical systems, and the first type is called a map, which has discrete time, otherwise called steps or generations. The equations of motion for these kinds of systems look something like this. Let me zoom in a bit. All right. Which means that if you have a state at the n+1 step, this state is actually given by the equations of motion at the state at the n step. In addition to maps, you have the other type of system, which is called ordinary differential equation, where time is a continuous quantity. Okay? This means that the equations of motion give the time derivatives instead of the next step, let's say. So this is what I'm talking about. So in both cases, this u, this vector, is the state of the system, which is actually the variables that define the system. And this could be really anything you can imagine, from positions to angle action variables to voltages and resistances and everything you can imagine. So let's see how we can create a simple discrete dynamical system in Julia. A dynamical system is a struct that has all the information necessary for the actual real dynamical system, which is the equations of motion, the initial state, the parameter container, and optionally the Jacobian. How do we do this? We use this constructor. So this constructor over here tells you that you create a dynamical system, a discrete dynamical system by using some equations of motion and some state and some parameter container. So what I will do now is try and create the Henon map, which is a very simple discrete chaotic system. And the first step, of course, is the equations of motion. And The equations of motion is a function. They are a Julia function that represents the actual equations of motion of the system. Now for the Henon map, this is the form of the equations of motion. And what I have to do now is encode this thing into a Julia function. And I can do this in two ways. The first way is using what we call out of place form, which means that the equations of motion is defined like this. You give it the state as a static vector, and it returns the next state again as a static vector. Static vectors come from the static arrays module, but they are also re-exported in dynamical systems. Okay, so this is the first way you can define this function. The second way you can define this function is what we call in place, which means that the function is defined like this, and given the current state, which is x, it operates in place into the new state, which is x new. Okay? And typically you want to use the out of place form for systems that have dimension less than 11. And by the way, as a side comment, if you are familiar with DifferentialEquations.jl, then you will notice that this is actually exactly the same way you would define the function in differential equations. So let's define the Henon map using the first approach, which is out of place, because the Henon map is only two-dimensional. So let me clear everything. All output clear. Okay. So the first thing I have to do, of course, is load up the library by using Dynamical Systems. And then I also have some plotting commands to ensure that everything is displayed nicely. And my first command is defining the equations of motion function. As you can see here, I define the function so that it returns a static vector. And the first entry of the static vector is this one, and the second entry is this one. And as you can see, this thing is exactly the first line, while this thing is exactly the second line. And remember that P is the parameter container. So in the case of the Henon map, this is the parameters A and the parameters B. So I define this function. And after I have defined this, I have to define an initial state. It doesn't matter that much for the Henon map, so I will just define it to be 0, 0. And the last argument I need is the parameter container, which is A and B. And it is always best for you to define the parameter container as a mutable object. So what I do here is I define it as a vector, which is indeed a mutable object. All right, so these three things that I have defined, the function, the state, and the parameters, are enough to create a dynamical system. So I'm calling up the constructor, and Julia says, all right, you have created a two-dimensional discrete dynamical system, and then it has some more information. Okay, so that's nice. And the simplest possible thing you can do with this dynamical system is get a trajectory out of it. So, excuse me. And to get to the trajectory, you call a very simple function, which is called trajectory. So you create the trajectory of any dynamical system up to time t. And this is what we will do now. We say, all right, give me the trajectory of the Henon map by evolving it for this amount of time. So when I run this function, it creates a trajectory of the map. And as you see, the type of the output is a dataset, and I will talk later on about datasets. But this is the trajectory. It has two columns because, of course, the system has two variables. And the other thing you can do is give a third argument to trajectory, and this argument is a different initial state. So here I will create again a trajectory of the Henon map, but I will start from a different point, and this is the result. Okay, so now to visualize this, I will just use PyPlot. This is my preference, and plot the trajectory by accessing the columns. So this syntax accesses the first column of this matrix, or it's actually a dataset, and this is the second column. So I do a scatter plot, and of course, as was expected, both trajectories fall on top of each other because the Henon system has an attracting set at these parameter values. And this is how you get a trajectory out of a discrete dynamical system. Now, before moving to continuous systems, I want to talk a bit about the Jacobian function. So let's look at the Henon system that we created once again. What you will notice is that there is this line over here that says Jacobian and then says forward diff. This means that the Jacobian function of the equations of motion was created automatically using the module forward diff. And the reason this is done is because the Jacobian is an extremely important quantity that we need almost everywhere in the library. However, you don't have to rely on automatic differentiation. If you want, you can define your own Jacobian function. And this you do with creating one more Julia function. And in the case of the out-of-place form, you simply create a function that returns a static matrix which contains the Jacobian of the system. So this is exactly what I do in this line. I define this function that takes the state of the system and then returns a static matrix. And then I can call again the discrete dynamical system constructor and give this Jacobian function as a fourth argument, which is what I do here, and create a new system. And now this system, as you can see, instead of having automatic differentiation, it has the new Jacobian. Now, forward diff is very, very performant. However, the hard-coded version of the Jacobian should always be faster, in quotes, because this assumes that you have written optimal code. And for two-dimensional systems, this is not very important, but for higher dimensions, this becomes significantly more important. All right, so now we have seen how we create a discrete dynamical system. What I will show you now is that the same process is exactly done for a continuous dynamical system. Everything is totally identical. And to show you what I mean, let's create this system, which is called Henon-Hales system, which is a continuous system. And for demonstration, I will use the in-place form of equations of motion. So how do we do this? Once again, we define a function that has the derivatives vectors, which is the left side of these equations. And I define it in place, which means that this function, as you can see, operates in place in the first argument, which is the derivatives vector, of course. And in the end returns nothing because it doesn't have to return anything. In addition, as you can see, this system doesn't have any parameters. So when I call the constructor for this system, I will not give it any parameters, but instead pass nothing, which is what I do here. I call the constructor continuous dynamical system to create a continuous system, and I give the equations of motion function, an initial state, and then nothing. So I do this, and Julia says, all right, everything's fine because you have created a four-dimensional continuous dynamical system. And this is it. And everything that we have done for the discrete system works the same way for the continuous system, which means that if I want the trajectory of this continuous system, I call the function trajectory, I give it the system, the time I want to evolve for, and I can also specify optionally a time step value for the integration. So I do this, and the result is again a dataset. And once again, I can plot this just like I did previously for the Henon map. And this is how it looks like. Now I want to add a comment about differential equations.jl. Discrete systems use some internal algorithms to be evolved. But however, all time evolution of the continuous systems uses the differential equations.jl library. And if you want to see the default keyword arguments that solve continuous systems, then you have to find this variable that states the algorithm that is used and also the default tolerances that we use. Now, it is almost certain that if you use DynamicalSystems.jl for the continuous aspect, you probably also want to use differential equations.jl, which is why there is this minimal interface that can switch between an ODE problem and a continuous dynamical system. Okay? Now, besides this, all arguments that you can give to solve of differential equations.jl can also be propagated to any function that accepts a continuous dynamical system. For example, I'm now using ordinary diffec to access some additional solvers, and what I want to do as well is to use some difference tolerance, oops, this should be rel tol, and some difference dt max. This is fine, I define these keyword arguments, and then what I do is I call the trajectory function by giving these extra keyword arguments. And if I press this, if I submit this, this will run, and it will have used a different solver, different tolerances, different DT max. Of course, however, now you will not see a difference when I plot this because, of course, the trajectory is almost the same. But in general, you could have differences. All right. So this is the end of the first notebook, the first tutorial, which is about how to create a dynamical system base. What I want to do now quickly is simply go into the documentation, and what I want to do, go into contents. I just want to show you the other features of dynamical systems base that you will not see during this tutorial for the sake of time, of course. So besides what you have seen, dynamical system base also creates some specialized integrators for dynamical systems that can either integrate trajectories in parallel in exactly the same time, or integrate the tangent space and renormalize the tangent space as well. But other than that, this is the features that you have seen in this tutorial. Okay, perfect. So now I will close this one and move into the second tutorial. So let me shut it down. I'm shutting stuff down because my laptop isn't really powerful, so it cannot really handle it. And now we will move into this part, which is called chaos tools. And let me clear the all output. All right, perfect. So we carry on. I hope everything is fine. Let me quickly check the chat. All right, I don't see anything wrong with the chat, so I assume everything is fine. I'm sure Matt will let me know if something is wrong. So at the moment, you are probably thinking that everything that I have shown you is trivial because you can already do it with differential equations.jl. And this is, of course, true. But the things you can do with this dynamical systems instance is much, much more than just getting a trajectory. Now, the simplest thing you can do is get an orbit diagram. So what is this thing? An orbit diagram is actually a plot that shows the long-term behavior of a discrete system as you vary one of its parameters. Now, to compute this is actually very, very simple. The way you do it is as follows. You have your discrete system and you first evolve it for some transient amount of time. You then evolve the system again, but also save the output for some chosen amount of time. Then you increment a parameter of the system, and you repeat all these three steps again. All right? So if you do this for many different parameters, you get the orbit diagram. And this gives you a good idea of the long-term behavior of the system. So what I will do in the following is produce the orbit diagram of the logistic map, which is something really, really famous. And once again, I have to use the library using dynamical systems. And something that I haven't discussed yet is that besides you being able to define the dynamical system you want, there is also a module that has many predefined systems, which is called systems. And one of these predefined systems is the logistic map. So I can just load it immediately without having to recreate it every time. All right, so this is it. Now, I want to create the orbit diagram, so there is a function for that, and has this call signature that says create the orbit diagram of this discrete system by saving the ith parameter of the ith variable of the discrete system and changing the parameter that has p index, and use the p values. So you have to give to the function what parameter values you want to use for. And then there are also some keyword arguments that denote how much transient time to have, and in general fine-tune the orbit diagram computation. So let's do this now. I define which variable I want to save, which of course for the logistic map doesn't make sense because it only has one variable. And then I denote how many steps I want to save and how much transient steps I want to have. I also denote which parameter I want to change, which once again doesn't make sense for the logistic map because it has only one parameter. But then I also have to define the parameter values I want to use. So I have each of these arguments over here. and then I call the function orbit diagram, and it gives me some kind of output. Now this output, as you can see, is a vector of vectors. Its inner vector has length n, this is n, and contains the values of the ith variable at the given parameter value, all right? Now, you see no output right now because the output of this function does not make much sense to see numerically. Instead, what one should do is plot it. So I have defined this function here that calls the orbit diagram function and then does some manipulation so that it is plotted fast. So I will define this function and then I call it. So this function creates the orbit diagram and then plots it, and this is the result. So what you see here is the orbit diagram of the logistic map. Now what does this mean? As I said, this shows the long-term behavior of the system. So for example, if I go to parameter value 2.5 and I check the orbit diagram, I see that at parameter value 2.5 there is only a single point in the orbit diagram. This means that the state of the system, at least in the long run, is a steady state, a stable state. The system goes to this point and never leaves again. It stays there forever. As I increase the parameter, something else happens. So for example, at the parameter value 3.2, if I go and check the orbit diagram, I see that it has two different points. So this means that the system is not staying at a single state, but instead is alternating between two different states. And if you continue to increase the parameter, you see that the same process happens again. And in fact, this is well known. The logistic map follows what is known as a period doubling route to chaos. So as you increase the parameter value, the periodicity of the system, so the states it goes through, is doubling again and again. It started with 1, it then had 2, then 4, and then it goes to 8, and so on until infinity. One other cool property of this orbit diagram is that it is a fractal and it is self-similar. So what does this mean? This means that if I take this thing as is, and now I will zoom in the parameter span of 3.5 to 3.6. So I will zoom in this tiny area. This is what I will do here. And what you will see is that the orbit diagram that you see in the full picture is actually repeated almost identically as you zoom in. So this is the fractal property of the orbit diagram. And before we move on to different functions, let me tell you that the orbit diagram function itself works for any discrete system. It doesn't have to be one-dimensional, it doesn't have to be out of place. Whatever discrete system you have, the function will work fine. So see the documentation page for more. Alright, so that was fine, and that was something for a discrete system. Now let's look into something that is useful for continuous systems. And this something is the Poincare surface of section. What is this? This is a technique to reduce a continuous system into a discrete map with one fewer dimension. So what does this mean? By the way, my description will be okay, but it's also good if you want to read the Wikipedia page on the Poincare map. So what does it mean to reduce a continuous system into a discrete system? It's actually pretty simple. So let me go a bit back. So you have the phase space of your system, all right? Let's say it's this box. And the system is evolving inside this phase space. It goes around. So what you do is you define a hyperplane in this phase space, let's say here. As the system evolves around, it sometimes will cross this plane. Every time you cross this plane, you record the state of the system, okay? And the system goes around again and again, it returns to the hyperplane again, and again you record the state of the system. And you take care to only record states that have a specific crossing direction. So you cross this way, but not this way, all right? So this defines the Poincare surface of section. And to define this theoretically, you need to also define this hyperplane that I mentioned. Mathematically, the hyperplane is defined with this equation. So U is the state of the system, A is a vector, and B is some number, and A and B are the parameters of the hyperplane, all right? Now, if you want to compute the Poincare surface of section of a continuous system, what you have to use is this function that is called Poincare SOS. In this function, you give a continuous system, you give the plane, and you give a final amount of time that you want the system to be evolved for, and then some keyword arguments. Now, this is the mathematical equation for the plane, and in code, you can define the plane with two ways. The first way is using a tuple of an integer and a number, and then the hyperplane is defined simply as when the jth variable, with j being the first entry of the tuple, so when the j variable crosses the value r, which is the second variable of the tuple. Now, the other way to define the hyperplane is to define an abstract vector that has length d plus 1, with d the dimension of the state space, and the first d elements are the a vector, while the last element is the b number. So let's put this to the test. I will create the Poincare surface of section of the Lorentz system, which is also super famous. So the Lorentz system is given by these equations of motion, and it's also in the predefined systems library, so I can just immediately call it like this. And first, let me show you how the phase space looks for this three-dimensional system. So it looks like this. This is how the Lorentz system goes about when it is evolved. All right? Now I want to take the Poincare surface of section about this, and I want to first visualize what this actually means. So I have some code here that we do not care about because it is purely plotting code. It has nothing to do with dynamical systems. The only thing we care about this code is the output, which is showing what the plane means. All right? So this is the phase space of the system, and this is how the orbit moves around. And then I define a hyperplane, which is this gray plane. And now every time the trajectory crosses this plane, I record a point, okay? Now, this demonstration uses both directions, but the function Poincare surface of section only keeps one crossing direction, not both ways, all right? So this is what we mean by a Poincare surface of section. So let's do this. We define the plane, which is when the second variable of the system will cross the value 0. And then we call the function Poincare sos. All right, we give it the Lorentz system, the plane, some evolution time, and then we let it run. And this is the result. And of course, as expected, the second variable of the system is almost 0 at the Poincare section. And now let me plot this, okay? So what I plot now is what's happening on the section, okay? So what you will notice is that this section looks like a one-dimensional object because it is composed of almost continuous lines, and continuous lines are one-dimensional. And so this is expected because, as I will show you in a later tutorial, the attractor dimension for the Lorentz system is 2, which means it's a two-dimensional attractor. So if you cut through a two-dimensional thing, you are expected to get a one-dimensional thing. All right, so that was fine. What I will do now is change the parameter of the system. I will change the parameter of the Lorentz system, which is what this function does, and plot the trajectory again. So what you see now is that we have changed the parameter and we are now in a stable regime. The Lorentz system is stable for this parameter value. So I want to compute the Poincare surface of section again for this system now, which has a different parameter. Of course, the only thing I have to do is not change anything because I have already changed the parameter of my system. So I call once again the Poincare surface of section identically as before, and it has 1710 points. And now I plot it. And this is how it looks like. And now, as expected, you see that this section is actually a collection of individual points. You see here 1, 2, 3, 4, 5. This means, because it's a collection of individual points, it has dimension 0, and therefore it's the original trajectory that I cut has dimension 1, which is true for periodic trajectories. And now what I do here is just compare the two Poincare sections side by side, okay? Just for comparison. So this was the Poincare surface of section. In general, it is a very useful tool, but now we will move on to something different, which is Lyapunov exponents. So another thing you can compute with DynamicalSystems.jl is the Lyapunov exponents. But first, let me tell you what this is. Because Lyapunov exponents are extremely useful in studying nonlinear dynamics and chaotic systems. So, for a system like the ones we study, if you take an initial, okay, I will go a bit back. So you see my arms? Yeah, you see the arms. So you take an initial condition somewhere here in the phase space. And what you do is you initialize a new initial condition very, very close to the old one. So you see this is like super close, super tiny close. And then you start evolving both of these two initial conditions in time, all right? At first, they are very close, they stay together. But as time increases, the two initial conditions go further and further apart until they are completely apart. Okay? All right. So, what the Lyapunov exponent does is measuring this separation rate between these trajectories that are initially close. That's it. The Lyapunov exponent is actually something quite simple. And with lambda, we denote the maximum Lyapunov exponent. Now, why maximum? Well, because a d-dimensional system has d exponents, and that's why you use lambda for the maximum one, typically. And in general, a trajectory is called chaotic if it has nonlinear dynamics, it is bounded, which means it doesn't go to infinity, and it has at least one positive Lyapunov exponent, okay? This is a simplification, but it will do for now. All right, so for a demonstration, let me show you what the Lyapunov exponent measures using numbers and not my arms moving around. So once again, we initialize the Henon map that we defined in the previous notebook and in this tutorial, and we create a trajectory out of this Henon map. I'm not plotting the trajectory, but I'm doing exactly what I did before. I just create a trajectory of the Henon map, which is this two-dimensional discrete system. Now, what I will do is initialize a state that is very, very close to the original state of the Henon map. And then I will create a trajectory out of it, okay? I also do not care about this trajectory because what I do care about is plotting how these two trajectories go apart. So what I will compute is actually the distance between the two trajectories. And this is what I will plot. So in the above axis, you see one of the two coordinates of the Henon map for the two trajectories, blue and orange. In the bottom plot, you see how their distance is increasing as I increase time, and time is actually steps for discrete systems. Okay, so you see that the distance is increasing, and because this is a semi-logarithmic plot, the distance is increasing exponentially. Now the maximum Lyapunov exponent is measuring the slope of this line, okay? So let's compute it. Now to compute the Lyapunov exponent with DynamicalSystems.jl is super easy. You just call the function Lyapunov, you give it a dynamical system instance and how much time you want to evolve, and this function immediately gives you the maximum Lyapunov exponent, which in this case is 0.42. Now if I plot a straight line with this slope, it should fall exactly on top of the distance of the trajectories, and this is exactly what happens. So what you see here is that this line is a line with slope the Lyapunov exponent, and it very well approximates what's happening here. So that's how you compute Lyapunov exponents. You just call the function Lyapunov. It's pretty straightforward. And if you want to compute many Lyapunov exponents and not just the maximum one, you call the function Lyapunovs that has an S at the end. You see it's plural. And once again, it's the same process. You give the function a dynamical system, you give it how much time you want to propagate it for, and this is the result. The result is the first exponent 0.42, the second exponent minus 1.62. Now, here comes the important part and what I believe is really nice with DynamicalSystems.jl. As I have already said, any function that accepts a dynamical system instance works for any instance of a dynamical system. So it doesn't matter if your system is discrete, if it is continuous, if it is in place, if it is out of place, etc., etc. The functions will just work. This means that I can just use the Lorentz system that I have used previously in this notebook, and I can just call the function Lyapunov on it and compute the Lyapunov exponent. And it just works, and the value is 0.9. And the same, of course, works if you want multiple exponents. So here I compute the entire spectrum of the of the Lorentz system by using the function Lyapunov's, and these are the three exponents that it has. Now for a reminder, just some minutes ago we were looking at these Poincare surfaces of section, all right? And what I was saying, without any proof, is that the trajectory of the system here is periodic because this is a discrete collection of points, while the trajectory here is probably chaotic because the entire thing is two-dimensional and therefore its cut is one-dimensional. Now, if my guess is right, the Lyapunov exponent for this parameter value should be 0, while the Lyapunov exponent for this parameter value should be positive. So let's compute this. Here is a simple loop that goes over two parameter values. It sets the parameter of the Lorentz system to the value I want, and then it computes the Lyapunov exponent, and then it prints it. It's pretty simple. So this is the result. And as you can see, the guess was indeed correct. The Lyapunov exponent for this case is 0, while the Lyapunov exponent for this case is positive, significantly positive. Now, I want to stress something which is very important, and this is that one has to be very, very careful when using these functions, like for example Lyapunov or Lyapunov's, because these functions are approximative methods. They do not give you a guaranteed result or a universally true result, not even by a long shot. This means that if you naively do a short computation or you don't have enough transient times, then this can lead to very wrong results. For example, I have the exactly identical code block as before with two differences. First of all, I do not evolve for an equally large amount of time. Secondly, I do not evolve at all for transient amount of time. Here I evolved for a large amount of transient time, but here for nothing. I run the computation again, and what you will see is that I find that the Lyapunov exponent value for the stable regime is 0.37, which is indicative of chaotic behavior. So if I was sloppy and I was just looking at this number, I would have a totally wrong idea of what's going on. All right. So these were the Lyapunov exponents. What I want to do now is benchmark how fast are these functions. So to do that, I will use the framework called benchmark tools. And for consistency, I will be sure to use these exact tolerance values. Okay. So to benchmark the function, I just call the macro btime and the function that I want to benchmark. Now be aware that this benchmark is using the default solver that we use in the library, which you saw previously, which is called Simple AddSheet 5, which is a simplified version of the adaptive version of the Chitonis 5 integrator. So the function requires 96 milliseconds to compute the spectrum of the Lorentz system, which is quite good, I believe. Now what I want to stress is that it is always important to choose a not correct solver. This is not perfectly fine. To choose a suitable solver for your system. What I will do now is benchmark the function again, but using a different integrator, which is called Vern9. And what you will see is that the Vern9 integrator is actually faster. This, of course, happens because it is not trivial to know beforehand which solver will be faster for your system. If you are more interested in this, please go into the documentation. I have an entire page just dedicated into this discussion. But anyway, what you see is that computing the spectrum of the Lorentz system takes 62 milliseconds from start to end. All right. Of course, it goes without saying that the functions for discrete systems are much, much faster. So what I do now is initialize a three-dimensional discrete chaotic system and benchmark exactly the same functions again. And of course, this will be much faster because discrete systems are much faster. So the Lyapunov spectrum for a 3D chaotic system requires 300 microseconds, while the computing only the maximal exponent requires 66 microseconds. Okay. I only have a closing comment now. So when I opened this video series, this tutorial series, I said that DynamicalSystems.jl is a library or a software library. So I didn't pay much attention to this, but this was meant in the literal sense, and now I will demonstrate why. So let's say that the function Lyapunov of a dynamical system, 2000 is too magical for you. You have a basic idea of what is a Lyapunov exponent. However, you still have no clue how this function actually computes this. And knowing exactly how a function computes things is really important for science. So to find out how this function computes things, we turn to its documentation string, which you access by doing the question mark and then pressing the function name. Okay, so this is the documentation string of the function. It starts by giving you the call signature and having 1 to 2 lines, the description of what the function does, which of course calculates the maximum Lyapunov exponent using a method due to Benetin, which simply evolves to neighboring trajectories while constantly rescaling one of the two, and capital T denotes the total time of evolution. So this is a pretty standard description, and then there is a listing of the keyword arguments. So these are all the keyword arguments that this function can accept. After this, there is this description section. Now, that in the description, we try to give a concise but complete scientific description of the algorithm. So let me read it out loud. It says, 2 neighboring trajectories with initial distance d0 are evolved in time. At some time ti, their distance either exceeds some upper threshold or is lower than a lower threshold, which then initializes a rescaling of the test trajectory back to having distance d0 from the given one, while the rescaling keeps the difference along the maximal expansion-contraction direction. The maximum Lyapunov exponent is the average of the time local Lyapunov exponents, and this is the formula. So, what's happening here is that this function tells you actually what we do. And of course, if you do not believe me that this is true, thankfully Dynamical Systems is open source, so you can just put me to the test. So this is important, and all documentation strings of functions exported by DynamicalSystems.jl have this structure. They have a call signature, then a couple of sentences that explain what the function does, then there is the keyword argument listing, then there is a scientific description of the algorithm, and then there are references, because of course if this paragraph is not enough, you just go to the original paper, which is where I got the algorithm from, and you are fine. Now I had here an idea to show one more algorithm, however I will not do that to save time. However, you can check out the Gali algorithm in the documentation page. But now for the interest of time, I will close this tutorial. So this was the first overview of chaos tools. I will return to this module later on. But for now, I will close this and close this as well. And I will move. By the way, do not worry, because this was by far the largest notebook. The next ones are much, much smaller. So if this was tiring for you, don't worry, a break is coming. So the next notebook talks about delay embeddings. So once again, cell, all output clear. So let me use dynamical systems once again. All right. So we will, one moment, sorry. So my throat is starting to give up on me. Let's hope some tea will help. Anyway, let's start by talking about how we handle data in this ecosystem. You might recall that in the previous tutorials I was computing some various data and they were returned in the structure called dataset. For example, Trajectory and Poincare shows both return a dataset. So what is this thing? Let me create a dataset out of random numbers here. Dataset is the structure that dictates how we handle data in the ecosystem, and it is just a vector of static vectors. It is actually a wrapper around a vector of static vectors. And besides being just this wrapper, it also has support for matrix-like indexing or indexing, how you call this. This means that you can access this dataset with two ways. If you access the dataset with one index, it acts like it is a vector of static vectors. Of course, each static vector is a data point, a row, let's say. So if I say dataset 1, this will access this dataset in the first data point, which is this thing. And if I access it with a range of 1 to 5, this once again will behave as a vector of static vectors and will therefore return a smaller vector of static vectors. In addition, you can iterate over this dataset. So you can say for point in dataset, do something. All right. Now, this is for one index. If you access the dataset with two indices, then it acts like a matrix where its row is one data point. Equivalently, it is accessed exactly like the matrix it is printed like. So imagine that this is a matrix if you access it with two indices. For example, accessing with 1, 2 will of course give me the first time point and the second variable of this data point. Accessing it with colon and then some integer will give me this specific variable's time series. So here the first variable of my dataset. And accessing it with two ranges will return again a dataset that is smaller. So that was it. That is what dataset is, but it was just convenient for us to have a specific data structure to use throughout the ecosystem. All right, so now we move on into something really cool, which is called delay coordinates embedding. So what is this thing? Why is it useful, and how can you do this delay coordinates embedding with DynamicalSystems.jl? So let's say that you have a real-world system which you measure in an experiment or so. You are assuming that the system has multiple dynamic variables. However, you can only measure one of them or some function of one of them. So you have a severe lack of recorded information about the system and you don't know what to do. So you might think that it's about time to give up on science because it's a complete waste of time. However, there is another alternative, to use Token Theorem, which at least in my eyes is indistinguishable from magic. So it should go without saying that we suggest to use the latter approach because science is really cool, you should never give up on it. So let me describe this theorem and the process revolved around it. If you have a time series S, you can reconstruct a state space, a multidimensional state space, by shifting this time series in time. What does this mean? This means that given S at some point n, you define a multidimensional vector z by having the entries being S at time n, S at time n plus tau, S at time n plus 2 tau, blah 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 blah, S at time n plus gamma tau. Okay? So, I will tell you later why this is useful, but how you do this is very, very simple. You just call the function reconstruct or the other equivalent function which is called embed. So if you have let's create a random vector here. So I want to reconstruct this vector using 3 temporal neighbors, so 3 of these entries, and this delay time, this tau, to be 1. And this is what I do. And of course, as you will notice, if you shift this column one index into the future, you get the second column, which is exactly true because this number is this number is this number. If you shift this column 2 steps into the future, you get the third column because this is this, and so on and so forth. So this is delay coordinates embedding, and this is how you do it, by calling the function reconstruct. Now, and as I said, this also returns a dataset. Okay, so now you might be wondering, well, why is this even helpful? Why should I even care? What's going on? The reason why you should care is because there is this theorem, which as I said, it's Token Theorem, that says that for a proper choice of these tau and gamma numbers, the reconstructed trajectory is homeomorphic with a true real trajectory of the dynamical system that you got S from. What does this mean? This means that many quantities, like for example the Lyapunov exponents and the dimension of the attracting set, are the same for the real dynamical system and the one we reconstructed here numerically. So even though we are clueless about how many variables the system has in reality, we can still get a lot of information about this system by reconstructing this. Now, isn't this just magic? How can this possibly be true? It is true, by the way, because it's a proven theorem. I'm just really excited with this. Okay, now I've shown you how to reconstruct signals. Let's see how this actually looks. So to see how this looks, I will initialize yet one more continuous three-dimensional chaotic system, which is called the Giesinger System. And I will now show you how it looks like in the phase space. So this is how the Giesinger System looks like. Now what I want to do is take one of the three variables of the system, take its time series, and then reconstruct it. And I will do this for all three variables of the system. So this system has three variables. I will reconstruct each one of them. Also, I will do these reconstructions for different delay times, so you have an impression of how these reconstructions look like as you change the delay time. And because we want to plot this, I will only do two-dimensional reconstructions so that it's easier to plot. So this is what this code block here does. It loads up the system, it creates a trajectory of the system, and then what it does, it is reconstructing each one of the individual variables of the system. All right? Now, the result is here. I think I have to zoom out a bit, right? Yeah, all right. I will zoom out a bit and then we'll zoom in again. So, this is what's happening. So as you can see, this row of plots is the reconstruction of the first variable of the system, and so on and so forth, while the columns are reconstructions for different delay times. Okay? Now, that's kind of difficult to immediately see, but if you are already familiar with delay coordinates, you can see that choosing the delay time value of 5 is actually a bad choice, and also choosing the delay time value of 100 is also a bad choice. I do not have time to explain why this is true, but what you see from this plot is that in general, some delay time value around 30 is a good estimate, all right? Now, let's say that you want something more than a good estimate and you don't want to use plots. How do you estimate this delay time? As I said, the proper value of delay time is really important, which is why DynamicalSystems.jl offers functions that can estimate both the delay time as well as the amount of temporal neighbors, which is the same as the embedding dimension. Okay? So for starters, or for this tutorial, we will use the function, or we will see the function estimate delay, which does the following. It estimates an optimal delay time to be used in embed on reconstruct, and using various methods. So the methods I will use in this tutorial is the first one, which finds the delay where the autocorrelation function becomes 0. The third one, which finds the first minimum of the mutual information of the signal with itself. And lastly, the fourth method, which fits an exponential decay to the correlation function. Okay? So this is what I will do. I here have the first variable of the Giesinger system to use as my time series, and I will estimate a delay using these three methods. This is what this loop does. It calls the function estimate delay. It gives it the time series I want to estimate the delay for. It gives it the method and optionally what delays to check. Okay, so I will run this code now, and this is the result. The result is, first of all, for the method of the zero of the autocorrelation, the value is 400, but you already see that the code failed because it already says as a warning that it did not cross the zero value, so the autocorrelation did not become zero, and therefore it just returned the last value of tau. The mutual information the mutual information minimum method gave the value 51. This is what you see here. And the exponential decay method gave the value 1116. Now, as you can see, the exponential decay method also failed. The reason for this is that these methods that use the correlation function are tailored to a specific form of a correlation function. One expects it to be oscillatory so that it crosses zero, and the other expects it to be exponentially decaying. So this is why they failed here. On the other side, the method that uses the minimum of the mutual information is always successful, or at least as successful as it can be, however is the most computationally costly. So let me give you an example of two plots. What I will do in this code is plot the autocorrelation and the mutual information, and this is the result. So as you can clearly see, the autocorrelation never crosses the value 0, so it makes no sense to try to search for its 0. And as you can see, it also does not decay as an exponential, so it doesn't make sense to fit an exponential there. On the other side, the mutual information has a well-defined first minimum in a value that we expected the delay time to be good or suitable, which is around 50. Okay, and the last thing I want to mention is that the method that we have for the mutual information is very fast because it uses an advanced to-be-published algorithm that improves existing standards. So for this time series that has 40,000 entries length, computing 100 mutual informations takes 0.3 seconds, which means 3 milliseconds per estimation of mutual information. All right, so this was a description of the delay embeddings module. What I want to do now is once again go to the documentation, which is here, go to the contents and say or list the things that I do not have time to go through in this tutorial. And the first thing is that besides a method to estimate the optimal delay time, you also have a method to estimate the optimal delay embedding dimension, which is called estimate dimension, and you can find it here. If you want, you can click, and it will bring you to the function. And there is also an interface to nearest neighbors that creates a neighborhood function that can be used globally across different datasets. All right. So this is the end of the third notebook as well. 2 more to go. So what we will do now is take a 5-minute break so I can check the chat and see if there are any questions. So if you have any questions, please do write them in the chat. I will see it and try to answer it. So let me pull up a timer. Can you see the timer? You can see the timer. So break 5 minutes. So this starts. I will mute me now and be back in 5 minutes. All right, break time is over. So we move on to the next part. The next part is about entropies and dimensions. So, okay, let me clear this notebook and then we can start. All right. So we'll now go into a different, let's say, method, algorithm, quantity, which is the generalized entropy. So in the study of dynamical systems, there are many quantities that quantify as entropies, and I'm not referring to the commonly known ones from the statistical physics point of view, which is the thermodynamic entropy. I'm talking more about the entropies of information theory, which represent information contained within a dataset. In general, the more uncertain or random a dataset is, the larger its entropy will be. On the other hand, the more predictable the dataset becomes, the lower its entropy will be. So, let's say you have an array of probabilities such that it sums to 1. Then you can define the generalized entropy to be this equation over here. So this equation is also called the Rényi entropy, and it generalizes other known entropies, like for example the Shannon entropy at alpha equals 1, which reduces to this expression over here. Now, given that you already have the array P, which is an array of probabilities, then it's pretty straightforward to compute the entropy. However, how do you get this probability array from a dataset? Well, this is simple. The way you do it is that you make a histogram out of the dataset, and then P represents the probability that a point of the dataset falls into a specific bin of the histogram. All right, that's fine. So, how do you compute this bin slash histogram slash probability array given a dataset? So let me create a random dataset over here. These are a bunch of random numbers. And if I want to directly compute the entropy of this dataset, I call the function genentropy, which stands for generalized entropy. So you give it the order that you want, then you give it a value epsilon, and the dataset you want the entropy. Now epsilon is the box size. Epsilon denotes how large will be the boxes that you will partition your dataset into to compute the probability array. So if I want this, I can straightforwardly compute the generalized entropy of order 2 of this dataset with box size 0.1. And you can continue doing this for smaller box sizes and smaller and smaller. Now what you will notice is that the output of the genentropy stopped changing after some epsilon value. The reason for this is that the entropy value has already saturated. So there is no use in partitioning the dataset in even smaller boxes. What you will notice is that this function requires you to give it a dataset, so it is very conveniently used with outputs of, for example, the trajectory or the Poincare shows, since they return a dataset. For example, let's say I want to compute the entropy of the trajectory of the towel map. So a towel map is a three-dimensional discrete chaotic system, which I load here immediately using the systems module. And then I create a trajectory out of this system. Actually, let me plot it in 3 dimensions. Plot 3D columns of this trajectory. So columns just separates the dataset into 3 individual columns, and then I give them all as individual arguments to plot 3D. Oh. Yeah. So this will probably take some time because I didn't realize how large was this n. So yeah, that's a lot of points. Let's forget about this. I plot it later on as well. But anyway, if I want to get the entropy of this dataset, I just call the function genentropy using the appropriate values, and I give it the dataset. All right. Now, the entropy of this dataset, how does it compare with the entropy of the random dataset that we defined previously? So as expected, the entropy of the random dataset is higher because the random dataset is more uncertain, while the dataset of a dynamical system is not that uncertain. Okay, so what I want to point out now is that this computation is fast. Of course, for 3 dimensions, you can always make it fast. However, in general, partitioning this dataset, creating a histogram, is in general a costly operation, and it also depends exponentially on the number of dimensions of your system. However, in this specific application of the entropy, we can tremendously reduce the memory allocation and time spent in computing this histogram or doing this partition. And we do this with a function that we call non-zero hist. So this function computes the probability array out of the partition of the dataset without creating an entire histogram. And so this is the result. I just call this function on this dataset with a given box size. And here is the sanity check that ensures that the results sum to 1. And as I said, this time this function is really fast. The important bit is not that it is fast now, it is also very fast if you use a 9-dimensional dataset. So this dataset is 3-dimensional, this dataset is 9-dimensional. So benchmarking always takes just a tiny bit of time. What can you do? And what you will notice is that the time difference is very, very small. The reason is because non-zero hist also uses a very specialized to-be-published algorithm, and its time complexity does not depend exponentially on the dimensionality of the dataset, but only linearly. And it also has a line arithmetic complexity on the number of points. All right, so now we have a way to compute entropies. How do you use this? Well, there are many ways to compute what is called a dimension of a dataset, like for example the fractal dimension. And most of the time these dimensions indicate some kind of scaling behavior. Specifically, the scaling of the generalized entropy versus decreasing box size gives the so-called generalized dimension. So you have an expression like this. So the entropy is approximately equals to minus d times the logarithm of the box size. And d is actually the dimension, or the generalized dimension, of the dataset. Okay? So let's compute the generalized dimension of the towel map. And now I also try to plot this map. So this is how the towel map looks like. This is of course a projection in 2 dimensions. And I have a lot of points here, but be aware that the more points you have, the more precision you have, but also the more computations you need to do. Anyway, to compute a dimension for this thing, what I have to do is compute the entropy of this thing for many different box sizes. So this seems pretty simple. First, I need some kind of range of box sizes. And I will start with a random guess, which of course is not random at all because I already know what to do, but let's say it's random. So we start with this guess for the box sizes, all right? So these are all the different box sizes I want to compute the entropy for. And then the only thing I have to do is make a loop over the entropy, which is what I do in this line, and then just show the result. So this is the result. For each value of the box size, I computed an entropy for this dataset. Of course, you don't need to write 5 lines of code to do this because Julia has this amazing broadcasting syntax. You can only do it in 1 line of code. However, be aware that I had to use here this ref syntax. I have to wrap a ref around the trajectory because the trajectory is also iterable, and I do not want to iterate over the trajectory, only over the box sizes. Anyway, so what we have now is some entropy values for some given box sizes values. And remember that it should hold that the entropy is approximately equal to minus a constant times the logarithm of the box size. So let's plot them and see what happens. So this is the result. This is the entropy. This is the minus logarithm of the box size. And as you can see here in the middle, there is indeed a regime, let's say, that the entropy scales linearly with minus logarithm of the box size. And what typically happens is what you see. There is some region that the scaling behavior holds, but then it stops holding true due to the finite amount of data points. So, above, this behavior holds between these two orange vertical lines. So what I do now is get my data only inside this regime, all right? This is what I do here. So I have these two curves, x and y, and what I want to do is simply fit a linear regression over this parameter regime, and this I do by using the linreg function from the module chaos tools. And this function tells me that the slope is 2, which means that the generalized dimension is also 2. And this is actually a correct result. The information dimension for the attractor of the towel map is around 2. Now we might have numerous questions. For example, are these values for the box sizes that we used good enough? How can I know? Or, for a general dataset, how do you estimate good values for the box sizes? Well, for this, we provide this function called estimate box sizes, which takes a dataset and then uses some heuristics to estimate the appropriate box sizes for this dataset. This function, of course, takes many keyword arguments, but I will not go through them in this tutorial. So, by calling this function, this is the result of the estimation. So I can now use these box sizes values to get the generalized entropy once again, and once again plot it versus the logarithm of the box sizes. And this is how it looks like. Of course, a general function with general heuristics will not work perfectly for any dataset, but will work decently enough for most datasets. Alright, now we go into the next part, which is the following. Given that you have this kind of relation between the entropy and the box size, is there any way to automatically deduce the scaling region and find its slope? This would mean that you automatically deduce the attractor dimension without having to look into this plot. And there is a way to do it, and the way to do it is by using the function linear regions. So this function takes two vectors, which mean that you have the value of y versus the value of x. And then it decomposes this function y of x into regions where the function is approximately linear. It then returns the indexes of x that correspond to the linear regions and the approximated tangents. So if I use this function and I compute the linear regions of the logarithm of the box sizes versus the entropy, this is the result. Now it's best to just visualize this result, although it's pretty clear what it means, but this is what the function does. It partitioned this curve into regions that are approximately a single linear region. So as you can see, all these 5 different regions are not collinear with each other, let's say, but all of these are, and they are approximately in a single linear region. So what you can do then is call the function linear region without an s at the end to directly get the slope of this portion over here, which is 2.08. And this is of course exactly the result that we obtained previously when we did everything manually. Alright? So let me summarize what has happened. The first thing is that we decided on some partition sizes, some box sizes, and we could use the function estimate box sizes to get these. Then for each box size, we computed the generalized entropy, okay? And we stored it as an array with capital E. Then what we tried to do is find a linear scaling region of the curve of the entropies versus the box sizes, and the slope of the largest linear region is the dimension we estimated. Now, wouldn't it be cool if all of these steps were possible with one function call? Yes, and this is exactly what the generalized dim function does. The generalized dim takes an alpha value and a dataset and then computes the alpha order generalized dimension of this dataset by doing these 4 steps automatically in one go. So we can use this function directly, or at least immediately, and it will give us the result 2.055, which is once again the correct result. Now what you see is that the automated process was not perfect here. In such cases, the function issues a warning so you can double check your results, and it also expands the limits of computation just a tiny bit to get a better estimate. But so far it has worked fine, and now let's use the same function for the Henon system, the Henon map. I hope you remember the Henon map that we have seen in the previous tutorials, and you can just initialize the Henon map and get a trajectory of the Henon map, and then get the generalized dimension of this trajectory for the order 0, and the result is around 1.21. So the generalized dimension, and actually this is the capacity dimension, for the Henon map is 1.21. Of course, as always, you have to be very careful. This function is only a crude estimate. You must check and double check and triple check your results if you want more accuracy. All right? Now, in the previous tutorial, or in actuality 2 tutorials before, I mentioned the Token Theorem, and then I said that for proper choice of an embedding time and an embedding dimension and a delay time, this theorem guarantees that some quantities, like for example the attractor dimension, remain same between the reconstructed and the original systems. So now we can show this numerically. So let's start with the trajectory from this system that we used in Notebook 3, which was the Giesinger system, and create a trajectory out of this system. So this is a trajectory with 400,000 points. And once again, we can estimate a delay time for this trajectory. And we already know this number. It's 52 in the previous tutorial. Now it's 53, pretty much the same. And then we can embed this trajectory into some higher dimension. Here I choose a dimension of 3. Now, using the generalized dim, I will compute the generalized dimension of order 1 of first the original trajectory and then the reconstructed trajectory. So let's see how this will fare. So the original trajectory has dimension 1.88 and the reconstructed has 2. And you can see that these two numbers are very close. So given the accuracy of our computation and the limitation of finite data points, I'd say this is still pretty good. Alright, so this was the end of this tutorial. We saw how you can compute entropies and dimensions with DynamicalSystems.jl. The last thing I want to do now is once again go into the features of chaos tools, because we will not be seeing chaos tools again. So I'm back into the documentation page, and I have to go to the overview section. So chaos tools has a lot of other functionality. For example, it can do automated production of orbit diagrams for continuous systems. It has a method to distinguish between chaotic and regular behavior. It has a way to estimate the Kaplan-York dimension, and there is also a method to compute the permutation entropy. There are some tools for nonlinear time series analysis like Broomhead-King coordinates, or a method to numerically determine the maximum Lyapunov exponent. And lastly, there is also a method to numerically find unstable and stable fixed points of any order for a discrete system, or so a map. Alright, so these were the features. So now I'm going to close this tutorial, or this notebook, and move on to the final one. Shut down in this one. Alright. Okay. So the final notebook is about also the final addition we had in DynamicalSystems.jl, which is recurrence matrices and recurrence analysis. So let me give you a quick background into this field. So most of the dynamical systems we have seen so far evolve within a bounded set. This means that instead of going away to infinity, they stay in a specific region of the phase space. Now, in such cases, a recurrence is an event that is very likely to happen, and in fact, most of the time it is guaranteed to happen. By the way, recurrence simply means that the trajectory, x of t, visits the neighborhood of itself at some point in later in time. So let's say that I started here, I go around, and after some time I'm close by to where I started. This means that you have a recurrence. And a recurrence matrix is a good way to list or to store those events. So to put it in more concrete terms, the recurrence matrix is defined as follows. The I, j entry of this matrix is 1 if the distance between trajectory at time I and at time j is less than some threshold value. Otherwise, the recurrence matrix is 0 at this entry. And of course, the distance between two data points means some kind of metric. You can use any metric you want, but in this tutorial I will be using the Euclidean metric. Or also this time series, this can be an actual time series, so univariate, or it can be a full trajectory. So let me give you some examples. Let's use again the Lorentz system that we used when we were talking about the Lyapunov exponents. So once again, I'm loading dynamical systems and some plotting stuff, and I initialize the Lorentz system, which is a three-dimensional continuous dynamical system. And what I will do now is create a recurrence matrix for this system. All right. Now, a quick reminder, you might recall that for this parameter value, the Lorentz system was stable. We showed this in the tutorial number 2. Or sorry, the notebook number 2. So I'm setting this parameter here because I want a stable trajectory. And then what I do is compute the trajectory of the Lorentz system for some time. And then, after I have this trajectory, I simply create or instantiate the recurrence matrix. So let me do this. All right, I think I have to zoom out just a tiny bit. All right. So this line computes a recurrence matrix, and internally the recurrence matrix is stored as a sparse matrix. However, it is displayed as a plot, as a Unicode-based plot. So each point in this plot is an entry of 1 in the recurrence matrix, and white space means that the recurrence matrix is 0. All right. So now I can zoom back again. Okay. So this is how it's displayed by default. However, plotting these matrices is actually very important, so there are many ways to do it. The recurrence plot function uses the text-based plot that you already see here, but there are other ways to do it. For example, you can get the coordinates of the non-zero elements and plot them as scatter data. So if I go to my Julia console and type, give me the coordinates of this recurrence matrix, then this will give me 2 columns of the points that are 1 for this recurrence matrix, while the points that are 0, of course, are discarded. And then what I do is I can simply scatter plot these 2 columns and get the recurrence matrix in a, let's say, higher resolution. Okay, so this is what you see here. This is again the exactly same recurrence matrix as before, but it does look a bit different. So I have to drink a bit of tea. All right. The other thing that you will notice is that the axes are in index unit. These are indices. This is not time. However, you can make them time units simply by taking these vectors and indexing into the time vector. For a trajectory, by default, the time vector is 0 to dt to t, which is what I define here, and then I simply access this matrix, this time vector, using the coordinates, and then I will get exactly the same recurrence plot, but now the axes are in time units, in proper time units. All right, so let me show you some typical recurrence plots for typical trajectories. And what I will do here, so you might think this is a lot of code, but all of this is plotting. The only lines that are from DynamicalSystems.jl are these 2, and these four. Everything else is plotting. So what do I do here? What I do is plot. I have to zoom out a bit. I'm plotting a typical trajectory of the Lorentz system for a periodic and chaotic regime, and below that I'm plotting the corresponding recurrence matrix. Okay? So the first trajectory is periodic, and as you can see, this is how the recurrence matrix looks like. Now this is intuitive because what this means is that, remember, wherever there is a point in the recurrence matrix, I have a recurrence in my time series or trajectory. So for at time, let's say that this is 3, at time 3, I am starting to be close to time 0. However, because this trajectory is periodic, if I'm close at a previous time point, if I increase both time points in parallel, I should stay close because I'm going into a periodic motion. This is why you have these diagonal lines over here that span the entire recurrence matrix. On the other side, if you have a chaotic trajectory, it's not the same story. What happens is that you typically do go close to a previous point in time, and you stay close for some time, but then you stop being close. And as you can see, I have some diagonal lines that are close for a bit, but they do not extend for longer times, and definitely not for infinity, which is what happens here. Alright, so this is how typical recurrence plots look like, and this is how you can plot them by calling the recurrence matrix and accessing its coordinates. Now, how do you use this recurrence matrix to obtain useful information for your system? Well, to do this, you use this pipeline that is called recurrence quantification analysis. There are a lot of measures that are defined based on the recurrence matrix, and depending on your application, some of them are more useful than others. And you can compute all of them by calling the function RQA, giving it a recurrence matrix, and various other keyword arguments that I will not overview. And this function computes a lot of different measures, all of them well documented, and this is a name tuple, so you can just access them by pressing dot and then this name. Now let me just talk about a few amount of them. So what I will do now is compute a few of them, which is the determinism and the divergence and the average diagonal line length, and then I will explain what they are. So as you can see, once again I loop over the parameters where the Lorentz system is stable and chaotic. I compute these RQA measures, and then I print some of them, okay? This is what this code block does. And the result is this. So as expected, in the discrete system, the maximum diagonal is much larger than the chaotic case, but in fact this number is meaningless because we already know for the stable system the diagonal lines are infinite. They are not finite. Of course, we cannot compute infinity here, but anyway. The other thing I'm interested about is the average diagonal line length for the chaotic case. Again, it should be infinite for the stable case, so we do not care. So what does this number tells us is that if you go and look back into this recurrence plot, all of these diagonal lines, they all have a specific length. What is the average length of these lines? And the reason you should care about this is because they tell you that on average, how long do trajectories stay together, all right? So for the chaotic case, this is 37. Of course, this is in indices. This is not in time units, all right? You have to multiply this with dt to get the real time scale. All right, so now I had a final example here that I wanted to talk about one more measure for the recurrence quantification analysis. However, because I'm running a bit short on time, I will skip this. Please be sure to go over this part of the notebook as well, or just read the documentation on this part. But for now, we'll close this notebook that was about recurrence matrices, how to compute them and how to use them. Of course, I will go into the documentation to show the features that I will not be describing. So the features I will not be describing is the fact that besides recurrence matrix, you can also compute cross-recurrence matrix and joint recurrence matrices. And also you can compute windowed versions of the RQA functions. All right, so this is it. This closes this tutorial as well. And now we go into the final part of this series. As you see, there is no notebook for this part. However, what I want to do is show off some interactive applications that we have been developing in the let's say last two months or so. So to do that, I have to open a different window. So I will just have the documentation website page show while it is loading. So these interactive applications are very new and they run on Mackie, which is a new plotting library from Julia that plots directly on the GPU, and therefore it's very fast and allows you to plot many different many millions of data points instantly. So this is kind of important for making snappy interactive applications for chaotic systems because you need a lot of data. And these applications, they are in a new Julia package that was just registered, but it's still in beta even though it's registered. And to find this package, you have to go into our Julia organization. Into our website, you go into GitHub. So this is the GitHub page of the organization. And these are all the packages we have. And then you find the package Interactive Chaos. So this is the package I'm going to demonstrate right now. It will take a lot of time to load, unfortunately, because at the moment it's beta and Mackie takes a lot of time to load. But I will be talking in the meantime, so don't worry. So I'm going to run an example. Let me run the example. Okay. So if you want to use these applications, once again, they are currently in beta, so be very careful. You have to install Interactive Chaos by typing add Interactive Chaos in your Julia session. All right, so now let me open up the desktop. I think you now are able to see. You are probably now able to see Atom. You are able to see Atom. Let me close Firefox. Okay. So let me zoom. Okay. All right, let me close these points. So we have to be just a tiny bit patient for the application to run, but it's totally worth it. So please stick around. Okay, it has to do some recompilation, but now we will wait. In the meantime, I can check the chat. Okay, there is nothing in the chat. All right, so now we are going to wait, and what I'm going to show you is an interactive application for exploring orbit diagrams. You probably remember from the first node, from the second notebook that I showed the orbit diagram of the logistic map. And this was a way to actually, let me show you this orbit diagram by going back here, clicking here, and going into the orbit diagrams. All right, so this was a way to visualize the long-term behavior of this discrete system, right? And what I said is that this object is fractal and self-similar. So if you zoom in, you actually see exactly the same orbit diagram being repeated. And this is really interesting. And at least for me, this was one of the first things that initially got me into working into this field. And this application that I will now launch will allow you to interactively choose a region in this orbit diagram and zoom into this region with increased resolution. So, yeah, unfortunately, there is some work that needs to be done in the pre-compilation process of Mackie and opening up a Mackie window. That's why we're still in beta, of course, because these applications, they run super smoothly and everything is very fast, but to actually start them from zero takes a lot of time, typically some minutes or so. So it's definitely on the list to start working on these applications. And of course, besides the interactive orbit diagram that you will see now, there is a second application that is part of interactive chaos, which is an interactive Poincare surface of section. So if I go back into the documentation, I have shown you the Poincare surface of section of the Lorentz system. This is once again a Poincare surface of section for a different system, the Henon-Heliès system, which we have also defined in this tutorial. And what happens here is that in these kind of interactive applications, you can click on the Poincare surface of section, and a new orbit will be created and evolved and going through the section. If we have time, I will show this as well. I think we have 10 minutes remaining for this tutorial. I'm not sure. But anyway, it's not that far. This what you see here is an electron window. The electron window will offer the controls for the interactive application, while the Macchie window will do the plotting of the actual thing. So now we're just waiting patiently for the Macchie window to open. Yeah. All right, while we're waiting, I'm probably going to set up a 2-minute timer so I can have some break to drink some water, because my voice is literally leaving my body right now. So let's put 2 minutes here, quick break. All right, so we're back, and now the application is working fine. So let me just scale everything. Can you see the window? No, you cannot see the window, but now you can. All right, so the way this works is pretty simple. Oh no, I have to run it again. Too bad. But now it will be instant, don't worry. Now we don't have to wait that much because everything is pre-compiled, or at least almost instant. All right, so I can barely fit this on my screen. Anyway, So the way this application works is that here you have the plot and here you have the controls. And you can click and select a region in this plot. And what this will do is interactively update the orbit diagram with higher resolution. And the good thing is you can really continue zooming as much as you want. So as you can see here, so now I have zoomed a lot. And the resolution is pretty crap. The reason for this is because I have to evolve my system for the orbit diagram for more time and for more transient amount of iterations. So I can do this here in the console, and then I can click update, and the orbit diagram is getting updated. And I can still continue zooming as much as I want. And once again, I need to run it for more time and also save more points. And once again, I can click update. And let's say I want even more points, and I can click update again. Now I added way too many points, but it's okay. This application also has history, so you can click back to go back, and you can travel through your journey into this orbit diagram, or you can click reset to go immediately into the original state. And you can also set the parameters you want in this box. So let's say I want to go from 388888 all the way to 4. I click update, and this is what happened. And one last thing I want to show, I will close this, is that as everything with DynamicalSystems.jl, this application works for any discrete system. So I will do exactly the same application now, but for the Henon map. So I will just use the Henon map, run this application again. Go here, okay, and this goes here. And this is the orbit diagram of the Henon map for one of the two variables. And of course, I can again continue zooming and exploring and increasing the transient time of evolutions and having history just like before. And one last thing to show, I will use yet another system for this, is you can interactively change between the variables of the system that you plot the orbit diagram for. Now, what does this mean? So now I create the orbit diagram for a different system. Oh, I have to run it again. We have some stability issues that I'm working on. Sometimes the electron window is not displayed properly. Anyway, so now you see here an orbit diagram for a system called the standard map, and the first variable of the system, which is U1, doesn't make much sense to use. However, I can change the variable to the second variable of my system and click update, well, what you see here is the orbit diagram of the second variable now, which I can still continue zooming, and I can still go back in history, and history also remembers the variables that you used. So that's it for the interactive applications. I'm not going to show the second interactive application because we don't have any time left. But you can check it out yourselves. So this was the end of the video tutorial. Please be sure to check out our documentation for more information. Check out our website for other packages of our organization. And if you use DynamicalSystems.jl, please start it on GitHub, because this gives me a good estimate of how many people actually use this thing. And you can do that by, if you are in the documentation page, you can go click here that says GitHub, and then you are brought into the GitHub page, and then you can start it here. So that's it. Thanks so much for watching. Hope this tutorial was helpful for you. If you have questions, don't hesitate to contact us. You can go into the documentation and find the contacting information, and you can contact us by joining the Gitter chat room or the Julia Slack chat room, or you can open issues directly on GitHub. So that's it. Thanks a lot. See you.